Hello and welcome to part 6 of Dev Maths and Stats Refresher Course, Lecture 9. Now we're going to look at the final distribution we have to consider, which solves an important problem. So we're on this demonstration here. The spreadsheet is not quite normal. And again, we're going to take lots and lots of samples of a normally distributed variable and look at how we can try and predict what's happening to the mean. So if we go to the spreadsheet, now this time I've put the samples like this in rows, and here I've counted the samples, and if you go down you'll see there are 10,000 samples. So there are 10,000 samples, they're all coming from a population. All of these numbers are generated by a normal distribution with mean 100 and standard deviation of 36. And for every sample I've calculated the sample mean, and the sample mean that's what we would have to use to estimate the population mean, because normally, even though I have generated 10,000 samples, normally you just go, you do your research, you get one sample, calculate the mean, and you want to know how close is this likely to be to this population mean, which is unknown. So to study this, we have to start with a situation where we know the population mean and see how much this sample mean varies. So for every sample mean, I've also given the error, the actual error. So that's the difference between the sample mean and the real mean. So you can see sometimes the errors are pretty big and low, sometimes they're big and high, sometimes they're small. And I've calculated the z value for that, which is the distance between the sample mean and the population mean divided by the standard deviation. But it is not divided by the standard deviation here, which is of individual values. As showed in the previous demonstrations, these sample means vary less than the original numbers. They follow a normal distribution with the same mean of 100, but the standard deviation of these is equal to the original standard deviation divided by the square root of the sample size, because the variance is equal to the population variance divided by the sample size. So the standard deviation is equal to the population standard deviation divided by the square root of the sample size. That's why I chose samples of size 9, because the square root of 9 is 3. So we just have to divide this 36 by 3. So the sample means they have a standard deviation here of 36 divided by 3 is 12. So it's 12. So to get the z-score, what we're doing is looking at this error and dividing it by 12, which is this divided by 3. That gives us a z-score. Then what I can do is, again, in this hypothetical situation where I know the population standard deviation, I can think of a number, anything at all, for example 120, and predict how many do I expect of these means will be above 0.66. Using the same method as before, so the z-score is that. The z-score for this, calculated the same way as these z-scores, is the distance between here and here divided by 12. 1.667. And then it's looking at all these here and it's counting how many are really above that in 10,000. It gets 500. The prediction is 4779. The actual counts is 500. And every time you press F9, it generates another 10,000 samples and sees how good is the prediction. So this prediction of 10,000 random variables is okay. It's in the right kind of area. But the whole thing collapses into nonsense, because we're doing this sample, maybe this is the sample you collect in your fieldwork. You only have these 9 numbers. You don't know anything else, but you want to use these 9 numbers to try and estimate the mean, and that's a pretty good one actually, though you might not know that. However, it would be the fact that if you could do this calculation, you know that only 456 out of 10,000 will be more than 20 away, so that's quite reassuring. So you're likely to be fairly close, within 20. However, it's no good because you cannot do this calculation, because if you do not know this actual population mean, it is very, very unlikely that you know the standard deviation of the population. So we do not know this. And if you don't know that, then you can't work out anything else. So all of these calculations can't be done. So because we don't know the population standard deviation, instead of that, what we need to do is, when you have your 9 numbers, you calculate the sample mean based on these, and you estimate the population standard deviation. And you estimate it using the sample standard deviation of these numbers here. So that's when you subtract the sample mean from each number, square the difference, add them up, and divide by 8, because there are 9 numbers. Divide by 8, and you get the sample standard deviation. So on the next sheet, I've done something along those lines. So what we've done this time, I've added 2 more rows, 2 more columns. This column here is it's worked out the standard deviation here, the sample standard deviation, so that's the estimates of 36. Then it's divided by 3 again, because we know we're talking about the standard deviation of the mean, which should be 3 times lower than this. So it's divided by 3, and that's called the standard error. So the standard error is the estimated standard deviation of the mean. Okay, so based only on the 9 numbers, you can get both these things. That's just based on the sample mean. That's just based on the sample standard deviation. And now, just with those 2 numbers, now you can make an estimate of, instead of a z value, it's called a t value. The formula is the same, which is the actual error between what the mean could be, what the mean actually is, and your answer from your figures, divided by the standard error. So instead of dividing by the unknown thing, divide by the standard error. And that gives you what would be a t-score, except now it's called, what would be a z-score, it's called a t-value because it does not quite follow the z distribution. It follows a slightly different distribution, not the normal distribution, a t distribution. So if we go back to the slide, we took many samples from the normal distribution. We know that the sample mean is going to follow this distribution, which is a normal distribution with the same expected value and the same standard deviation, except divided by square root of n. So in our case, that was square root of 9, which is 3. That's why we keep dividing by 3. And I showed that for any distance, I took 20. You can predict very accurately what percentage of the sample means are going to be within d of that population mean. So I said less than 20 over, using the tables or using the built-in function in Excel for normal distribution. That was fine, but I also showed you that it does not work if you do not know sigma. So how can we do this if we don't know sigma? And the answer is that we have to use the sample standard deviation instead of sigma, do the same calculation, but then you get, instead of a z distribution, you get the t distribution. If you plot those t distribution numbers, that's the final one we're going to use, you can see that the shape is pretty much the same as the normal distribution. In fact, to the naked eye, it looks exactly the same. If you do it on the same scale, actually it's slightly fatter, just that the scale here is slightly higher, so it's stretched up. So it's very, very slightly fatter. The other thing about the t distribution is, like the chi-squared and the f, there's different versions of it. As the sample size increases, the t distribution changes slightly, and it becomes, the bigger the sample size, the closer this t distribution becomes just to a normal distribution. So we'll see examples of that. Oops, try and find the slide. Sorry. So what you can show is that if you start with z that follows a normal distribution, and this follows a chi-squared distribution, then t follows this distribution. So t is the ratio between a z distribution, a normal, when divided by something which follows a chi-squared distribution. You can show that that approximately follows a t distribution. with what's called n-1 degrees of freedom. And degrees of freedom is similar to the idea with chi-squared and F distributions, that they're built on a certain number of random variables. And so if you calculate this, then T will follow a T distribution with n-1 degrees of freedom. So if you compare that with the Z formula you had before, it's exactly the same as the Z formula, except that the sigma has been replaced by the n. That means that for any distance you can predict what percentage of sample means are going to be within any distance of the population mean using the T distribution tables. So that's the theory. When you've seen several examples, it'll be much more easy to understand than just by looking at the theory. But we'll close this lecture by looking at a wonderful demonstration online next. But for now, thanks for watching.